And it is 3 o'clock. So let's go ahead and get started. Thank you so much, everyone, for joining the LPI virtual seminar. Our guest this week is Dr. Scott Sanford of NASA Ames. Scott has worked at Ames for over 30 years and is one of the leaders of the astrochemistry and astrophysics laboratory. He was a co-I on the Stardust, which is Discovery mission, which he'll be talking about now, as well as on Hayabusa and OSIRIS-REx. So definitely a leader in the field of bringing us back as space rocks to study. So he will be giving a talk on the Stardust mission and the power of sample return missions in general. So if you have questions during the talk, please feel free to type them into the chat, and we will answer them in the last 15 minutes or so of the talk. If you'd like to ask a question directly, you can also note that in the chat, and I can ask you to unmute your mic. Otherwise, please leave your microphones muted during the talk, and we will have question time afterward.
Yeah, just a comment. I don't mind being interrupted in the middle if there's a question that really should be answered right away, or it'll be pointless to ask later.
Okay, yeah, that works. With that, please take it away, Scott. Thank you so much for joining us.
Okay, well, yeah, thanks for having me. I'm always happy to talk about Stardust. I think my title's a little different from what you had on the announcement. I added the power of sample return missions to the end of the title to give me some latitude to extend the discussion a bit beyond Stardust. And if we have time, I'll, for example, be able to talk a little bit about OSIRIS-REx. But the main focus of the talk will be Stardust. And I'll largely focus on the things we learned from Stardust while the Stardust mission was active. I won't be spending a lot of time on things we've learned from the samples since then, but I will be making a point that that's one of the values of sample return missions. And I think this was already posted on the original announcement, but just a quick heads up, I will show some red and blue anaglyphs during this. So if you have 3D glasses, it'd be good to have them ready. I won't spend a lot of time on them because I don't want to make this an annoyance for folks who don't have the glasses, but I will show some. So I'm going to begin with a sort of shameless advertisement for sample return missions in general. This isn't specific to Stardust, but sample return missions allow you to do things that you can't do with normal missions where you do flybys or rendezvous. And of course, one of the advantages is that since you're returning samples to the Earth, they're available for current and future studies. So the value of the mission extends well beyond the end of the actual official mission. And also, since you're bringing the samples back to Earth, you can use state-of-the-art, up-to-date, latest analytical techniques and equipment. So you get the sort of ultimate in current precision, sensitivity, resolution, reliability, whatever you need. Whereas if you fly a spacecraft someplace, you're using the technology that was deemed to be acceptable to fly when you left. Also, the analyses can be iterative and fully adaptive, so you're not limited by current ideas. So for example, if you fly a mission to a planet and you have to decide ahead of time what your instruments are going to measure, and if everyone agrees that measuring the value of A is the most important thing, then you put an A measuring device on the spacecraft, but it may be that what you learned from that device is that you need to now measure B. And so if you need to measure B, you've got to make a whole new mission. But if you brought the sample back, if you measure something in the A lab and it tells you need to know B, then you can go down the hallway to the B lab and get on with things. And of course, you avoid limitations associated with cost, power, mass, and reliability because you're not limited by what you can launch on a spacecraft. Your sample measurements are made on the ground. And so some of the instruments, for example, that made measurements on the return Stardust samples weren't just bigger than the Stardust spacecraft, they were bigger than the launch pad from which the spacecraft left. So you're not restrained by those kinds of constraints. And then analyses can be replicated and verified, and you can calibrate. And I mean, this is kind of a fancy way of saying, once you have the sample back, multiple people can measure it and then they can argue about it. And that's a great way to progress science, is to have people bounce ideas and data off of each other. So when you have a sample return mission, effectively the payload of the spacecraft becomes all the world's analytical instrumentation. So that's a massive advantage for sample return missions. And here's just an example of some of the kinds of techniques that have been used on return samples, and many of these techniques would be very hard to do in situ. For example, down here at the very bottom, something like a synchrotron, you're never going to fly to a comet, but you can bring the sample back and take it to a synchrotron. And again, sample return is good because if you have a sample, then you can measure its composition, and this provides you all kinds of information. I'm probably preaching to the choir for many of you in the audience, but when you have the sample and you can get its composition, you can get an understanding of the conditions under which it formed, what the original starting materials from which it was created may have looked like, the evolutionary history of the object from which the samples came in terms of hydrothermal alteration, space exposure, impact exposure, etc. And you can often learn the chronology of major events in the object's history. And if you just fly to a place and measure there, you can only measure compositions through remote sensing, which imposes some really serious limitations on what we can learn. I mean, if we were on opposite mountain peaks and we're observing each other remotely, I might be able to learn things like you like to wear a red shirt and you eat lunch around noon, but I'm never going to know your blood is based on hemoglobin until I come over to your mountain and stick a needle in you. So if you can get the sample back, you're far less limited in the kinds of things you can learn. And so if you're someone like me who's very interested in the original materials from which the solar system was made, then is what you really like the most is sample return from small objects like asteroids and comets, because they do a reasonably good job of preserving much of their original material from which they're made. Most of the mass left over after the solar system formed is in the form of planets. And don't get me wrong, I don't think, I don't dislike planets. They're a great place to set down your beer when you need to get more potato chips. But if you're trying to find out what the raw material from which everything was made looked like, going to a planet isn't a very good idea, because that material has all been subsequently processed by being subducted into mantles, spewed out of volcanoes, weathered, paved over by Caltrans to make a freeway or whatever. Whereas if you can get samples from comets and asteroids, they will have suffered far less of this parent body alteration, and therefore give you a much better clue of the starting materials. And we do get samples from comets and asteroids for free in the form of cosmic dust, which can be collected in various ways, including from the upper atmosphere. And in the form of meteorites. And so we've obviously learned a lot about the early solar system on the basis of those kinds of samples. But they do have the disadvantage that even though they're captured, they've arrived almost for free, they're orphans. We don't know where they came from, so it's harder to relate what we learned from them back to any individual parent body. And so the advantage of a sample return mission is you can do all the things you would do with a meteorite or cosmic dust particle you collect, but you also know where it's come from. And so you have the context of the material with its actual parent body. So here's the Stardust spacecraft being prepared for launch. It was a Discovery mission, so it's a modest scale mission. You have people here for scale. It's about the size of a VW Bug or something. It's not a gigantic spacecraft. Just point out a few things in the picture. This thing at the top here with a white heat shield on it, this is the sample return capsule. So this is the only part that actually came back to the Earth, and this is where the sample, after it was collected, was stowed. The solar panels in this picture are all folded up. In this other picture over here, you can see the panels folded on one side of the spacecraft, unfolded, so you can get a sense of what it looked like. And this is the comet we went to. It's 81P Wild-2. It looks like it's, you would pronounce it wild, but it's Wild. It's named after a Swiss gentleman who discovered it. He actually was an astronomer who was interested in finding supernova, and he had an automated telescope that searched for changes in the sky and would flag them as potential supernova. And one day his alarm went off and he saw there's a little dot that shouldn't be there surrounded by a fuzzy patch, and he was sure he had a supernova going off in a galaxy. So he ran back to the telescope to confirm, and the whole galaxy had moved to the left, and so he realized he had a comet, which is still a cool discovery. But we actually invited him to come out to the launch for the spacecraft because we thought he would enjoy, that we were going to a comet he discovered. And he did enjoy that, but in discussions with him, it became quite clear that he was still kind of hacked off that it hadn't been a supernova. So I guess to each his own. For me, the comet would be more interesting than the supernova, but for him, it was clearly the other way around. Stardust was also candy bar. I don't know if any of you saw these, but during the period when Stardust was going to fly, Nestle's came out with 9 limited edition bars that had 9 different spacecraft on them. and Stardust was one of them. So, and the image of the spacecraft is not quite right. In particular, we did not have the word crunch on the solar panels. But one of the team members on the mission, Mike Zelensky, thought it would be cool to give one of these candy bars to everyone on the team. And so he went out and bought them. But the way they came in the box was all 9 were mixed together. You couldn't tell which one you were getting. So in order to get us all a Stardust one, he had to buy them until he got a Stardust one. And then he rewrapped it and taught himself how to feel through the wrapper, whether it was a Stardust one or not. And then for the next couple of weeks, apparently, he would go into the store and feel up all the candy bars and find the Stardust ones, and so that he could buy those and give them to us. So I'm not sure which disturbs me the most about this, whether Mike would spend the time to do that, or whether I'm more disturbed about the fact that the store didn't seem to call him on standing there fondling all the candy bars. But anyways, so for a brief time, Stardust was also a candy bar. So Stardust went to Wilt 2 for 2 reasons. I mean, it was a very good comet to go to, and I'll explain why it's a bit unique as a comet. But the main reason we went is because we could get there. And the reason we could get there was because it's in an orbit that actually is part of what made it interesting. Prior to 1974, Comet Wilt 2 was in an orbit, which is the yellow oval here, which went well out past Uranus. And then when it came back in, the closest it got to the sun was Jupiter's orbit. It was probably in this orbit because it had probably had an encounter with Jupiter in the past. But in September of 1974, it had another encounter with Jupiter, which shifted it into this inner orbit, which is shown here in red. And so the current orbit has its aphelion near Jupiter, but its perihelion is actually not too far out of Earth. So this means that Jupiter basically delivered the comet to us, or at least it brought it most of the way. And so that makes it much more possible to get there without needing, massive rocket motors and so on. So now I'm going to go to a plot where we've zoomed in. So now this is Wilt's current orbit, and the yellow orbit here is the Earth. And this is, so just so I can describe the trajectory we used to get the comet. We launched in '99, and we went into an orbit that just took us around the sun and brought us right back to the Earth later. So we could do an Earth gravity assist, which boosted us into a new orbit that crossed the comet's orbit here. And so on the second orbit we got here, but unfortunately at that time, the comet itself was way over here someplace. So we had, in this orbit, we had to go all the way around the sun again. And then on the third orbit out, we were able to meet the comet here, capture our sample, and then return back. And then the Earth was here when we came back, and we could drop off the sample return capsule, and the spacecraft was left to go back out into space. So this required we do 3 orbits. And during those 3 orbits, we traveled a total of about 2.88 billion miles. So that comes out to an average cost of about 7 cents a mile. For those of you who are civil servants will know that that's well under the allowed per diem for travel. So that's great. One other thing I'll point out about this orbit is even though the main point of the mission was to get here to the comet and get samples, we also had a secondary science goal, which was during the infall part of the orbits over here, we're actually moving in the same direction as interstellar dust entering the solar system. And so during this part of the orbit, we would have the minimum encounter velocity with this dust as it ran us down from behind. And so we tried to capture that dust on the backside of the collector from which we got the comet dust. And most people don't know this, but the original inception for Stardust, and hence its name, was to actually do this interstellar collection. And it was only on a later proposal that we added the comet to the mission, and that's when we got selected. So this interstellar dust collection was actually the original inception for the mission. Okay. Oh, and just to point out that, so we left, in terms of the sample return capsule, we left from Florida when we launched in 1999. And after all of these miles, this sample return capsule came back and landed in Utah in 2006. So, just to be honest, there is an easier way to get from Florida to Utah. MapQuest here shows you at least one alternative way to do that. And so for the sample return capsule anyways, despite the long distance traveled at high velocities, its average terrestrial velocity was only about 0.04 miles per hour. So you could have probably watched the launch and crawled on your belly to Utah and watched it land without any real trouble. I'm not going to talk a ton about the spacecraft itself, except to point out a couple of key features. we were not a rendezvous. We did not go to the comet, stop and get dust and then move on. We did a flyby, and we did everything we could to minimize the velocity during the flyby, but it was still over 6 kilometers per second. That's something like Mach 20. So I don't know if any of you have ever run into something going Mach 20, but I'm sure it stings. And in fact, one of the biggest issues for our spacecraft is that if we ran into a largest size particle at 6 kilometers per second, it could destroy the spacecraft. So most of the leading edges of anything that had a direct view of the comet were protected by Whipple Shields, which consist of a thin metal plate, a series of Nextel curtains, which are kind of like the material used in bulletproof vests, and then a final thin metal plate. And the idea was that particles that hit this front plate would be exploded into pieces. They would penetrate, all the pieces would then hit the next layer, penetrate that, but be broken down further, and every layer would slow things down, break the particles into smaller grains. And in this manner, you could protect yourself from a fairly large impact. The Whipple Shields we flew probably could have protected us from things about the size of a centimeter. Anything bigger than that would have caused us big trouble. And it's a good thing we had these, because our dust flux monitor told us that we were in fact hit by a few things that were big enough that had we not had the Whipple Shields, we would have been in real trouble. Only a few things peeked around these Whipple Shields. One is when we were collecting the dust, the aerogel collector actually lifted up out of the sample return capsule and peeked over the top of the shield. And then we had a periscope right here, which could look at the comet as we approached. And then if dust grains hit the mirror and wrecked it, we would still be able to take pictures as we flew by, because the camera, which is down here at the bottom of the telescope, could rotate this lower mirror and follow the comet as it went by underneath us. And so this allowed us to take pictures of the comet coming and going, even if dust grains impacted with the front optical element. We also had a mass spectrometer target plate here. I won't talk about this instrument any, but that was one of the other few things that peeked around. And then this is the sample return capsule. It's a clamshell. It opened up like a clamshell to let the collector deploy, and then it was done, it all tucked back in, and then the clamshell closed. And then this is the only part that came back to the Earth. So, so how did we collect material while we were going 6 kilometers a second? That was only possible because we used a material called Aerogel, which is essentially fluffy glass. It's, I think it's in the Guinness Book of World Records, the lowest density solid in existence. It's, you just have thin silicon dioxide type filaments like glass, and a lot of empty space between them. And that allows you to achieve a very low density. And that low density then becomes something you can impact a high velocity particle into and expect it to have some chance of surviving. So, so for example, if you had 6 kilometers a second, you take a particle and you run it into, let's say, a plate of metal, like in this picture down here in the lower right. You form an impact pit. The impactor is largely vaporized. Most of the material is lost. Some material may remain behind in the crater, but much of that will be severely altered. So you will not do a very good job of sample capture. But in the case of aerogel, you decelerate over a larger distance, and the material has a better chance of surviving. And if you look at these three images here, you can see the effect of going to lower and lower density aerogel. The particle can penetrate deeper and deeper. That means it slows down over more time and space, and therefore suffers less damage. And I think most people sort of have an intuitive sense for this. I mean, if I said I want to do an experiment where I'm going to take all of you and have you jump into one of 2 different buses, and then I'll follow get you out onto the freeway in these buses, and I'll follow in a separate car. And then once we're up to speed, I'll call you on the radio and let you know that in the interests of science, I've cut the brake lines on both buses. So, but don't be alarmed, this is for science, so it's all good. And then I said, don't worry, I've arranged for both of the buses to stop without brakes. And I told you one of the buses is going to stop by running into a massive pile of pillows, and the other was going to run into a brick wall. I think you all know which bus you would want to be on. And it would be the bus that takes the longest distance to slow down. And so that's what aerogel is basically doing for you. Okay, so when we did the flyby, we took images of the comet, and I'll show some images, including some 3D images in a moment. But we had on the front shield of the spacecraft a dust flux monitor that could measure impacts. And this graph in the 3D plot in the lower right shows a summary of the output from that. So the axis going from left to right is time. So at time 0 is the closest approach to the nucleus. The vertical axis is the number of impacts, and this horizontal axis here is the size of the particles. So you can see we got hit by a very small number of large particles and many more small particles, and that they were mostly centered around the closest approach, but we also got a number of very small impacts later on, which suggests either we flew by a second chunk of something that had come off the comet or passed through some, for whatever reason, some other concentration of material. But on the basis of this, we were quite confident that the aerogel collector must have been struck by, several thousands of grains bigger than 5 to 10 microns. So we were confident we were going to get a sample back, so that was a big relief. Just a few things about the nucleus itself. We flew by, we only had enough memory to take about 70 pictures, and since we didn't know when closest approach would be, we had to space them out over time. And as a result, we only got 7 or 8 images that were from fairly close to the nucleus. And then we also were splitting our images between long and short exposures. So the short exposures give you a good image of the nucleus, so you can see what the surface of the comet looks like. And the longer exposures overexposed the nucleus, but gave us a sense of what the coma looked like. And you can see both that the surface was extremely rough and complex, and that there were many jets of material coming out of the nucleus. Presumably these are dust grains being accelerated out by the loss of volatils. And there's a lot of really interesting landforms here that are not, that are unusual. So your brain wants to tell you, since you're familiar with lots of astro pictures, that all of these circular things are craters, but in fact, very few, if any of them, are craters. They're mostly probably landforms created by the sublimation of volatiles in the nucleus. So for example, if you look at, I've lost my cursor here, there it is, okay. This thing here, your eye first tells you it's a crater, but if you look at it carefully, you see it has a very flat, smooth floor, and it's surrounded by vertical cliffs. I'll show this in 3D in a later image. It is just not the shape of a normal crater. So it's most of the stuff you're seeing here in terms of the geomorphology is associated with devolatilization of the nucleus. So just as a kind of a comparison here, here's Wilt-2 and then several asteroids more or less to scale, and you can see the difference in the way that the things that look circular like craters are. There's a very distinct difference here. And Wilt-2 is actually unique, not just when you compare it to asteroids, but when you compare it to other comets. Most other comets show much more smoother surfaces without all of these kinds of details. And that's probably because these comets have been around the sun many times. They've lost a lot of volatiles, so you're seeing a very heavily reprocessed surface, whereas Wilt-2 may have only made close passages of the sun since it was injected into its current orbit in 1974, so it's had far fewer apparitions. So we may be seeing a much higher fraction of something that was similar to the original surface, and that in fact, as we devolatilize and lose a lot of that material, we may end up creating a new surface, which mostly looks like what we're seeing in the bottom of this depression here, where we've already lost volatiles, which is this smoother terrain, just like you see over in the other comets. Okay, so if you have your 3D glasses, now's a good time to put them on. In this particular image, you can see, for example, that this depression here has got very steep sides and a flat bottom. This is not the kind of contour you associate with a normal crater. And so you can see it's a very varied surface with pinnacles of things that stick out. Lots of pits of various sizes, ridges, and so on. And then you can see that there are jets that come out from both the night and the day side, and that some of the jets seem to emanate from some of the deeper pits here. Here's another view of it where you can see that overall the nucleus was shaped a little bit like an extremely fat hamburger patty with a big bite taken out of it. One thing I'd point out here on this end, this big depression actually has a sort of spire in it. You can even see the shadow of the spire in the background. This is probably also just due to the way, due to sublimation, how you get a spire like this, but you don't see things like that forming on an asteroid. And then here's a close-up of that one crater just to demonstrate that you have this very flat floor, very steep edges. There are even places where you may have overhangs of the top surface, and like, for example, here, this whole thing may be almost a bridge here. And so it's possible that there's a tougher material, which was the original surface, possibly tougher because it was processed by radiation for a long time, and that when you get underneath that, then you have other materials which can be sublimed more readily. Okay, so you can take your 3D glasses off for the moment now. If you want to leave them on, I won't know, but it won't help you see anything any better. I'll warn you when you need to put them back on. So after we captured the sample, we cruised back to the Earth, and we dropped off the sample return capsule at the Utah Test and Training Range in Utah. So in this area out here. And some advantages in landing at the UTTR is it's highly instrumented airspace. Things don't arrive without people knowing about them and being tracked. There's a lot of flat terrain with very little vegetation, so you don't have to be too smart to recognize sample return capsules lying on the ground. A lot of trained personnel to help. There are very few buildings or people to land on. You don't have to worry about someone getting there before you and stealing the hubcaps off your spacecraft. But there are some disadvantages. It is, a dry lake bed is kind of an oxymoron. It can be a lake or it can be dry. And even when it's dry, the water table is right below the surface. So there is potential for standing water, which can be a problem for your return capsule. And there also, then since this is an active military training place, there is always the potential for unexploded ordnance. One of the last nightmares I stopped having associated with this mission was the nightmare where we survived our 2.88 billion miles of travel, and then in the last 6 inches landed on an unexploded 500-pound bomb. But fortunately, that did not happen. So here's a picture of the capsule coming in over Wendover, Utah. I have a little movie here I can show, which was taken from the hyperseed flight. So these are images taken from a plane. This is the Pleiades up here, and you'll see the capsule will start to show up right here. So I don't know if you can hear the sound that goes with this or not, but it arrived to the fraction of a second that was anticipated, and that's a good thing, because if it was off by even a fraction of a second, it would have been at the wrong angle, and it either would have burned up coming in or skipped back out of the atmosphere and lost. So that all had to go perfectly. You can see it gets brighter. At some point here, you'll start to see a hint of the tail, the plasma tail behind it right here.
Cool.
And just as it's going out of sight at the edge of a window here, just as a kind of little perk, you see an actual normal meteor go shooting across the sky in this direction here. I always thought that was rather poetic.
Yeah, plasma lines have been detected.
There goes your little meteor right up there. So I saw that whole thing from a helicopter that was going to recover the SRC. So we found it. It had landed on the ground. Everything had worked well. It landed on its nose cone. You can see the mark on its nose cone. And it was in a crosswind, so it bounced and flew through the air and landed on its edge. And in fact, here you can see one of the landing marks from landing on its edge, and it rolled across the desert for some distance. Here you can see the track where it rolled. So it rolled like a quarter on a table, and eventually laid down on its backside of the back shell and rolled in a circle and came to a halt. So, so it had a little bit of a trip on the ground, but it didn't come down in water, and it came down whole, and so that was all good. Here's some footage shot as we got there, and in some of the images you can see the track very well. So here you can see the track moving off into the background there. And we obviously came down at night. It was a little bit surreal because on the dry lake bed, the only thing you could see was the immediate area illuminated around you. Okay, it was then put in a special bag so we could keep it from getting further contamination, loaded into a helicopter, taken to a temporary clean room in a building at the UTTR, where the back shell on the heat shield could be taken apart, the sample canister could be removed and put in a nitrogen purged container, and then all of these parts were subsequently loaded into a C-130, flown to JSC, moved into a clean room that had already been prepared for it, and opened up. And when it was opened up, it was so clean that there was some thought that maybe it had never actually opened at the Comet. We hadn't got anything, but after we could inspect it more carefully, we could see there were definite impacts in the aerogel cells in the collector. And so here we see Don Brownlee giving us the Viva Victory sign when we realized we really did honestly have cometary dust. So, and in fact, here's a close-up of part of the collector, and you can see marks on the front of the aerogel where larger particles slammed into the aerogel. We also collected dust material where grains ran into the frame that holds the aerogel. Here's an example of one of those craters, and some of these craters do contain material. And within the aerogel, we found sort of several kinds of tracks. Here's an image of a piece of aerogel from the mission, and this edge here is the front edge of the aerogel, and you can see there are some tracks that we call carrot tracks, which is a long thin track, and at the end of the track is a single grain, like a mineral grain, and that just punched its way into the aerogel. But many tracks look like this. They have a large bulbous area and then individual things that come out the bottom. So instead of looking like carrots, they look like, I don't know, ginseng or something. And so this is a strong indication that some of the grains that hit us were single sort of monolithic mineral grains, something strong, but that many of the grains that hit us were composite aggregates of things that when they hit actually broke into pieces. So they weren't held together very strongly. And that a lot of that fine grain material then ended up punching out this bulb, but there were some included stronger grains that then could continue onward and stop at the end of their trail. So that meant that individual grains that hit us were often dispersed over a large distance in the aerogel. So the samples, so we had a preliminary examination period at the end of the mission, after which all the sample was, that wasn't used, it was turned over to the curatorial facility so that they could then distribute it to others over time afterwards. So I'm gonna, just since I'm talking about the mission itself, I'm gonna talk about some of the things we learned during the preliminary examination when the mission was still active. Obviously, lots of things have been learned since then because the samples continue to be studied and they will be for decades to come. So there's plenty of other lessons that are going to be learned from the sample, but I'm going to focus just on the PET for the moment. And there are several issues of science and meteoritics and planetary science where you could go back to look at those original papers if you'd like. So I'll just hit some highlights here. But just to give an example of the sort of the progress you get when you bring back a sample. Over here is a woodcut of a comet taken in 1858, and over here is an image of the atomic spacing of a return sample. This is an increase in spatial resolution of a factor of something like 10 to the 15th or something. So the kinds of questions you can answer with the sample in your hands obviously far exceed what you can do remotely. So one of the big things that came out of getting the samples back is we found out that the Wilt-2 is a repository of largely unprocessed protosolar nebular materials. So the individual grains contain distributions of minerals and organics, which varied both in abundance and composition, and were heterogeneous both between different particles, but even within individual particles. So they clearly represent an unequilibrated reservoir of materials. Here's just one example of a grain that has a large iron sulfide grain, which was the front end of the particle as it came in, and that helped protect all this finer grain stuff behind it. And there's some ancestite material, but also fine grain material that contains all kinds of components, which on the whole have basically solar composition and then include organic materials. There's a big blob of organics down here. It's not so obvious in the picture, but, and so this strongly suggests that the materials got very little parent body processing in the comet. Otherwise, all of these things would have interacted with each other in a much more obvious way. And so, so that does tell you that the comet's done a pretty good job of preserving the pristine stuff from which it was originally assembled. But in addition, if you look at this wide heterogeneous mixture of stuff, you find out there's a truly wide range of materials. You have very high temperature minerals, like this mineral here is something that would be one of the first things you would predict to condense out of a gaseous nebula of solar composition, all the way down to organics that contain isotopic anomalies that tell you that they probably were processed in the protosolar nebula or even in the interstellar medium before the protosolar nebula formed. And there's no way these things could have been made in the same place or at the same time. And so it tells you that things were, the components had very different histories and somehow got mixed in the protosolar nebula so that they could all end up in the comet formation zone and get together, and then the comet did a good job of preserving them after that. So there's a strong indication then that there's a lot of mixing going on in the early solar nebula. It was not something where things stayed in their lane. Organics are present and varied. Some of the organics look very similar to the insoluble organic matter, which dominates primitive carbonaceous chondrites. But there's clear evidence of materials which are not so obvious in comets, including materials that are very rich in oxygen and nitrogen and that are less aromatic and more volatile. So this plot down here shows a Zane spectra of a number of organic areas on different particles, and you can see there's a wide range in what the spectrum looks like in terms of whether there's a lot of aromatic or very little aromatic. And if you look at a plot of the oxygen to carbon versus nitrogen to carbon plot, you find out most meteorites are down here in the corner. Primitive meteorites are a little bit higher up, but the Stardust samples and the average of IDPs we collect in the stratosphere are even further up. So there's a component here which is not frequently seen in most meteorites. And these materials are quite complex. Here you can see a mass spectrum of aromatic species, and there's just hundreds of lines here. So there's lots of molecules around. And the variability in terms of the chemistry is kind of phenomenal. If you look at the carbon to nitrogen ratio of different portions within grains, you find out that not only is the distribution different from one grain to the next, but here's a particle in which you have materials where the nitrogen is less than 1% of the carbon, but there's material where they're almost equal in abundance, which kind of blows my mind. The chemistry that's pretty restricted. And glycine has actually been identified in the return samples. So there are a wide range of organics. Unfortunately, hypervelocity collection is not a great way to get organics. They're far more susceptible to alteration and destruction, and I'll come back to that in a second. In fact, I'll come to it right now. If you take images of tracks and then you measure them spectrally in the infrared, you'll find out some tracks show no evidence of organics anywhere around the track, whereas other ones have a large halo that extends well beyond the track. And so the implication is that a grain containing organics hit the aerogel, and as it plowed through the aerogel and was heated, a volatile component evaporated off the grain and diffused into the surrounding aerogel and recondensed. And so this tells you that when you're looking at the actual grains, you're not measuring everything that arrived. And so this makes it very hard, for example, to come up with even the basic value of what is the organic to mineral ratio, because the organics simply didn't survive as well, and in many cases were redistributed. And so the hypervelocity impact collection has obviously got some limitations. It causes some real fractionation effects in your return sample. One of the, I think, big things that a lot of people have been wondering about was what would be the abundance of circumstellar and interstellar materials. I mean, some people thought that comets might consist entirely of interstellar materials, and that you might see huge proportions of circumstellar grains, pre-solar grains. And they are present. You can hunt for them using the same techniques you hunt from the meteorites, and you can find them. But their abundance is not extremely large. It's probably similar, it's basically similar to meteorites as near as we can tell. And so this sort of shut down the idea that comets might be, in fact, agglomerates of interstellar materials. They're clearly protosolar materials. They've been very well stored in a pristine fashion, but they are not you're not carrying at any more abundance than in meteorites, the pre-solar stuff, or at least not a whole lot greater abundance. But protosolar, circumstellar, pre-stellar things are present. We clearly contain, the samples clearly contain things that fall on the CAI mixing line. You do find things that have deuterium and nitrogen-15 enrichments, and pre-solar grains, in fact, are found of the same types you see in meteorites. There's one of the pre-solar grains that people think come from red giants or AGB stars, for example. These kinds of materials are present, but they're not dominant. For the deuterium and nitrogen-15 enrichments, the enrichments seem to follow carbon, not water. So the implication is that these are carried by organic materials, and we do see the same sort of small-scale deuterium and nitrogen-15 hotspots you see in meteorites. So these indicate the presence of an interstellar, protostellar molecules that predate the formation of the comet and then survived its subsequent lifetime. So the return samples do contain circumstellar and protosolar and interstellar materials, but it's in much the same manner as primitive meteorites. Sort of as a summary of the top list, there's a close association of really unequilibrated phases. And this implies that there was a lot of mixing going on in the early solar nebula. And that comets, even though we associate them with the outer solar system, contain materials from both the inner and the outer parts of the protosolar nebula. And that once they got together in the comet, they weren't reprocessed to any great extent. So they do represent pristine material in the sense that they preserve the characteristic nature of the original material from which they were made. Of course, that material preserves lots of other different histories, some of which involved, getting them very hot and so on. So the individual components are not pristine in the sense that whatever they used to be has been lost, but the assemblage is certainly pristine. And then I had mentioned earlier that the original idea behind the Stardust mission was to capture interstellar dust grains. And we had the aerogel tray was designed so it had a front tray of thicker aerogel to collect the comet dust, and then a thin tray on the back side to collect interstellar dust during 2 of our orbits when we were moving in the direction of the stream. And so we used we used a public to help us search for the tracks by making it possible for them to view images taken from the back tray to look for tracks. And so we had a number of very dedicated people who refer to themselves as dusters who scanned just tens of thousands of photographs, and we could do statistics on their performance, and they did a fantastic job. And they found a number of tracks that were potentially interstellar grains. And so NASA funded a special consortium to study those. And we found, so most of the impacts on the backside ended up being, came in at the wrong angles into the aerogel to be the interstellar grains. And if you tracked the angles back, you found out that most of them led back to the spacecraft. So a good fraction of the impact of the tracks on the backside were actually impact debris that was shot off the spacecraft when it was hit by interplanetary dust particles. But these could be distinguished from potential interstellar ones because they came into the aerogel to wrong angles. But 7 candidate interstellar particles were found where the angles were about right, and we were able to measure. They're very small, but we were able to measure things from them and find out that they vary. They're not all identical. The interstellar grains are not all the same thing, and so they all diverge in one way or another from sort of the generalized model of interstellar dust inferred from astronomical observations and theory. So we still got a lot more to learn about that. 7 particles isn't much to base an understanding on, particularly when they're this small. But it was really nice to see that the original conception for what Stardust should do actually worked. So that was a great thing. Okay, so that's it for my Stardust talk, and I'm happy to answer questions now. I do have some slides I can show about the OSIRIS-REx mission if there is interest, but maybe I should pause and find out if there are questions associated with Stardust first.
Thanks so much, Scott. If you have questions, please feel free to type them into the chat and I will read them off, or you can request to unmute your mic and ask them directly.
And if there aren't questions or you'd like to hold them, I can show a few things just associated with OSIRIS-REx, but I'll hold off until I'm sure.
Oh, hi. Could I speak?
Yes.
You said the solar nebula was extremely well mixed. Where does this leave the idea that we're now thinking that asteroids were formed in true well-separated reservoirs of carbonaceous and non-carbonaceous material?
Yeah, well, so the mixing had to have been really quite complex, and in fact may have been different depending on the nature of the materials you're talking about, particularly their sizes. Okay, so the typical grain size of Stardust materials is, the individual grains you're seeing are rarely bigger than microns. So we're truly talking dust. And so it's conceivable that you could have had a period where very fine-grained things were mixing over large ranges. And that's how you got the material that the comets ultimately formed from. But that as the whole system evolved and you started making bigger things, including things like protoplanets, that you would have started to have additional gravitational effects to start segregating material and keeping it from migrating in whatever manner it was migrating before. And so the mixing, clearly at the time when the comet was gathering up its components, had to have been sort of the full scale of the disk. But it doesn't mean that that mixing had to have continued for the entire lifetime of the disk in that manner. That full scale mixing may have been shut down at some point. And then you had much more localized mixing. And that's the period when you maybe made like the asteroid parent bodies. And I'm kind of speculating here because I don't think I completely understand. Certainly I don't understand how the models would predict the mixing evolve. Okay, so the mixing that ended up giving you the composition that made Built 2 may have differed in very distinctive ways from subsequent mixing, which defined what you ended up with in the asteroidal parent bodies.
Okay, thanks.
Ann Nguyen has a question. What do you think about possible in situ formation of chondrule-like material found in wild 2 samples in the outer solar system through high velocity collisions?
So yeah, well, so people have been arguing about chondrules since before I was a graduate student, and that's prehistory practically. So, and it's not clear to me that there's still a real agreement on where chondrules come from. In the case of Stardust, since we know we mix stuff from everywhere, you could have potentially ended up getting chondrule-like materials from anywhere in the nebula because they mixed there after they were made by whatever process made chondrules already for like meteorites. And of course, I know one of the possibilities for making chondrules has been suggested is that you get them in impacts. I'm not an expert on this, so I can't say yes or no, but if there was a lot of processing into chondrules by impacting on the actual comet parent body, then I'm not sure the comet parent body would look quite so pristine as it does. On the other hand, we only came back with a couple thousand grains, so it would be very silly to assume those 1,000 grains are representative of the entire nucleus of the comet. So you can't say that, no, there couldn't have been an impact on the comet that made chondrules that then ended up landing on the comet elsewhere, and those were the ones that were subsequently ejected and recollected. So you certainly can't deny that as a possibility. But given how utterly pristine most of the material looks, I don't think I would expect a massive processing of the comet nucleus was likely. That most places probably did not get processed in that manner. But again, I'm not a chondrule expert, so I'm not going to commit myself to saying yes or no to anything. But certainly we already know from what we do see that Comet has to contain materials that mix from all over the place. And so there's no reason why the chondrule-looking fragments couldn't have gotten into the comet in exactly the same way by being formed somewhere else and then mixed in.
Great. I have a question from Project Amane. What does Stardust sample analysis tell us about the timescales of accretion of comets like Wild 2?
That's a great question, and I don't think I can really give it an answer. I have to say one of the, I guess I won't use the word frustration, but one of the things I would love to have seen is the Stardust samples are so fine-grained that it hasn't really been possible for people to do any of the kind of chronology stuff that people frequently do with meteorites. You know, you take one of the radiogenic systems and you try to either get relative time scales, you know, do iodine, xenon, or whatever, or to get absolute scales to figure out the timing of everything. But when most of your material is in submicron grains, it's kind of hard to find materials where you can count enough atoms to do that kind of thing. And so, so there's really not a lot of chronology associated with the samples so far. And so, for example, I mean, I just talked earlier about how maybe the comet was formed during a period where mixing was disk-wide, and that later on that mixing stopped and other bodies were formed after that. You know, that the asteroids were basically formed later than the comets. But we have nothing from the samples we've examined so far that give us timing for the Wilt-2 samples that tells us that was the case. You know, the individual materials all look very similar to what we find in meteorites. And so at least the individual grains could very well have been made in exactly the same times and ways as the stuff that ends up in the meteorites. So one of the reasons I think NASA has on their priority list for the decadal surveys for New Frontier missions as a comet surface sample return mission is that Stardust allowed us to learn a lot of stuff, but we could learn a lot more if we could go down and come back not with, you know, micrograms of material that hit us at high velocity, but relatively pristinely, gently collected grams of material, if not kilograms of material. Because that would very much increase the chance that you could find components that you could actually physically date using traditional radiogenic techniques.
Speaking of techniques, Dan Adamo has a question. Can you cite any productive Stardust sample studies which would not have been possible at the time the samples were returned?
Yes, in fact, one of the things I did just partly to amuse myself is, you know, so when you pitch a mission, you write a proposal, and if you're down selected to be in the phase A study with one or two other missions, then at the end of that, you give a TIMCO presentation where you have a day to present the details of your mission to a review panel that goes over all the details and, you know, with a fine-tooth comb. And during the Stardust TIMCO, I gave a short talk on some of the analytic techniques we would use to study organics in the return samples. And so I had a slide describing the techniques we would use. And then, of course, we took off and ran the mission. But to build it and fly it took, you know, over a decade. And then it came back, and we, of course, measured it with all the latest analytical devices. So I went back and I compared the measurements we actually made on the samples to what I had put in that original slide. And I think only 2 of the 10 things I listed were actually used. Everything else had been surpassed by something better. And so this goes back to one of the advantages of sample return missions I mentioned earlier, is that when you're studying the sample, you're using contemporary instruments, not ones that were mature enough 10 years before to be worthy of being risked on a flight. Because I mean, when you fly an instrument to a body, you're not always using the latest technology. You're using the best technology you can fly. And sometimes that's a little older technology because it's more robust. So yeah, there are lots of examples just from Stardust alone of using techniques to study the return samples that were only gleams in people's eyes at the time the mission was selected. And in fact, this will continue into the future. I mean, if in 20 years someone invents a new technique, psychic infrared spectroscopy, you don't have to fly a mission again to use that technique. You can take the samples out of the curatorial facility and use this brand new technique to study the samples and learn, you know, a whole set of new things. So it's really one of the main, you know, one of the main powers behind sample return mission.
Tony Farnham has a question. How complete was the search for the particles in the aerogel, especially with respect to the IS particles? Did enough people look through the samples thoroughly enough that you feel that you caught them all?
Well, so for the Comet side, the approach is very much like most curatorial things. So that some of your samples just set aside. You don't mess with it all at once because you figure that in the future you'll know better. And so you process things and remove the samples a bit at a time. So we have certainly not exhaustively found every track there is on the Comet side. On the Interstellar side, the searching, last I heard, about half of the aerogel had been searched in the manner that we used to find the first 7 particles. So there may still be more particles, but in fact, there's some indication now that we might actually have better ways to scan it, and that we want to actually go back and rescan some of the stuff we've already scanned. So there's, I think, a decent chance that given time and effort, we will find some more interstellar grains. It won't be Just going on the statistics of the first pass of the first half, it's, we might expect to maybe double the number of particles, something like that, but we're not going to increase the number to thousands of particles.
So speaking of processing the aerogel, John Littleton has a question. How do you take profile images of impacts in aerogel? Is it necessary to cut through the aerogel to obtain a close-up image?
It depends on the size of the track, but one of the things that we were able to do, in fact, after the launch, was to practice how to handle things in aerogel. And so we would take things like light gas guns and fire analog materials into aerogel tiles, and then practice trying to figure out how to extract particles. And there are several ways to do it, but one of the ways, since aerogel is mostly empty space, it's not the world's strongest material against poking, basically. And so you can sometimes remove a track by simply using a micro-controlled needle to poke around the track and just sort of bust out the aerogel around it. You can just dig out a track, and then you can remove the track as a sort of pie slice of aerogel. And then some techniques, like doing some synchrotron techniques, you can simply measure the material while it's still right there in the aerogel. In other cases, you can try, if the grain's big enough, you can try plucking it out with micro manipulators and just pulling an individual grain right out of the aerogel. Or alternatively, in some cases, you can do things like impregnate the wedge of removed material with a material like epoxy, and then once it's solidified, do sort of traditional microtoming techniques where you slice down through the particle and you end up with slices of the particle. And then you can then measure individual slices using transmission electron microscopy or whatever you want. So there's a variety of ways to deal with the material in the aerogel. In a few cases, is what you do is you just take a lump of the aerogel and you treat that. So for example, I showed you that image of the infrared halo around a track. There was presumably cometary material around the track, outside of the track. And so you could, in principle, take some of that aerogel and try to extract that material using solvents or something. And in fact, the glycine that was detected was not detected associated with a specific track, but that was associated with material, divorced from any individual track. And so that may have been glycine that was vaporized from a particle and got into the rest of the collector, or it could have been stuff that maybe arrived in the gas phase because we were flying through the coma and ended up being collected. It's not clear. So there's a variety of techniques for removing the materials, and to some extent, the one you want to use depends on what kind of measurement you want to make and whether you've got it, whether aerogel being present is going to be a problem or not.
I have another question from Project Amane. If there was another comet sample return mission, what new information about comets would you want to prioritize other than chronology that Stardust could not achieve?
Well, I think, there's a number of things. Anytime you get a sample, and this doesn't matter what technique you use, there are going to be selection effects, right? It's almost impossible to get something that's truly representative of everything. But I think one advantage of going back and doing a comet surface sample return would be getting more material would give you a much better opportunity to see how materials are related to each other. So for example, if I get onto the OSIRIS-REx slides later, I can show you that there are clear distinctive differences in the material on asteroid Bennu that are at size scales that will not show up in a collected hand specimen of meteorite on the Earth. And so, by definition, you can't see structures in the material that are bigger than the materials you've got back, at least not very clearly. You might see some contact boundaries or something. So if you could go down and get more material, then you not only have a better chance of finding materials adequate for chronology, but you would be able to do a much better sort of petrography in terms of finding out the interrelationships of things. You would be able to do a much better job of getting the relative proportions of things. And in particular, one of my big things is organics. If you could go down to the surface and get a sample, instead of doing it at hypervelocity, you could collect all the organics that are present without cooking them first. And so you would get a much better handle on what their absolute abundance is, and also a much better understanding of the population of materials prior to any kind of thermal processing or impact processing. So getting a surface sample where you collect it at velocities of centimeters per second instead of kilometers per second would result in more material, better preserved material. You wouldn't have aerogel to deal with, would get in your way and make you worry about contamination and so on. So a surface sample return would be fantastic, and it wouldn't even it would just let you do a lot of things that we'll never do with Stardust because of the nature of the way we had to collect the material. I mean, the Stardust mission was fantastic. It allowed us to learn a lot of things that changed our vision of the solar nebula. But you can do better if you throw more money at it.
Great. Thank you so much, Scott. It's 4 o'clock and I don't see any additional questions in chat, so I think we'll go ahead and wrap it up there. Thank you so much, everyone, for coming to the LPI Virtual Seminar this week. Thank you so much, Scott. That was a fantastic talk. I know it's sometimes hard to get a sense for the audience appreciation on the formats, but
I hope some of you laughed at my jokes. I can't tell, so hopefully.
Yeah, I did for sure. But we really appreciate you being here. So the seminar series will continue next Thursday with featuring Dr. Carolyn Vanderbogert of the University of Munster, who will be talking about the dating of lunar features. So please look forward to that. We will be sending out an announcement for that shortly. Thank you again, Scott. Everybody have a great day.
Thanks, everybody.